Hey folks, so I'm going to talk about rasters today to hopefully not bore you too much. I know it's a lot, so just as a heads up, be prepared. It's a lot of data, lots of information. Okay, I'm going to share my screen so you can see slides. So you should be able to see, let's see, can you see my slides? Yes. All right, so we're going to talk about the raster model today. This is chapter 6. So a raster, remember, is basically a picture, um, and it stores information in all of these little cells. So we have columns going up and down, and rows going left to right. Each square has an X and Y location, and it can be georeferenced to the Earth's surface. So what does that mean? It means that it has a like a Latin long, basically, and you can, excuse me, you can slap it on the Earth somewhere, and it makes sense. Awesome. So each pixel or cell has a numeric value. A lot of times it's 30 by 30 meters, but whatever that number is it's the resolution. So it's always squared. So you can see that when you look in the spatial resolution information under properties. But it's really important when we're measuring something like elevation or rainfall. The values can be integers or floating point numbers, which is something you can understand when you're looking at an attribute table, which not all rasters even have. It usually only has one attribute, and so it stores a whole bunch of values um, in like one square. So you'll have two columns that will say something like 724 of 10. So that means that there's 724 squares that have the number 10 and the value 10. So it's a little confusing after learning about vectors. So why do we use it if they're confusing? It's because they're better at storing certain kinds of data. It's much easier to analyze data with them. Um, a lot of times you can do this a lot faster, and it's definitely great when you're using it for imagery or things like think about tree cover. Elevation would be tricky to do with vector. You can like topographic maps, but the hard part is coordinate precision is a little bit tricky sometimes. It's not necessarily as precise, and you can't store multiple attributes generally. So here's a couple examples. You're going to use something called the digital elevation model. If you took like an aerial photograph, you do this for land use, different kinds of roads. If you scan in a topographic map, and all of our ArcGIS base maps online tend to be rasters. So you have continuous rasters, like elevation or temperature. And that's a little bit different than imagery, which is a continuous raster, but it stores what's called brightness or reflexes. Because remember, it's taking a picture and it's shooting light down, and whatever reflects is what it captures. So you don't have to know all of these things. You don't have to be a pro at all this stuff, but you just need to understand what the basics are, so that way you kind of understand like what you're looking at. We have discrete rasters. So they do store some data, like categorical data, like land use or features, like roads. Um, a lot of these have been converted from vectors, so you can convert your vector layer to a raster layer. And the reason you can do that is we'll get into this down the road is when you lay rasters on top of each other. Um, but again, you can only store one attribute. We have raster tiles, so you can do this by think about it as a map, and then you're cutting up the chunks. And each tile is considered its own raster image. It's nice when the map is really complex. You can just grab tile by tile. A lot of times you'll see this done if you're downloading tree data. You'll grab a tile layer so that you can get little pieces of it. Sorry, I'm trying not to be making gross noises. You can see the differences in resolution. So when we are zoomed out to 90 meters, this is what it looks like. When we have 10-meter resolution, this is what it looks like. So remember, the pixel is defined in the resolution of that raster. and the precision is really limited by the resolution. So what does that mean? When you zoom in, it might get fuzzy. Okay, so that's the resolution in and out. Think about it that way. Um, base maps are great to show large areas at high resolution. This is what you do when, in order to do this, you have multiple layers, and each layer is shown at the appropriate scale. So you'll notice if you ever zoom into your base map, as you zoom in, you start to see more and more detail, right? And as you zoom out, it's bigger and bigger. That's kind of how that works, and that's with any picture that you're looking at online. Excuse me, sorry. Um, Pyramids are built just to have the display a little bit easier. You can use lower resolution copies um, for adjacent pictures, and it kind of helps put them together. It does take a long time to do this when you're setting it up, but it helps a lot with storage size. This isn't something you have to worry about too much. You can also do something called resampling. So say you have a raster image on the far left, it's kind of blurry, and you want it to be sharper and you want to see better. So you change it from 30-meter resolution grid to 40 meters. That's this black outlines here. You can make sure that you have a rule to determine the new cell value. So you can kind of see how the resolution has changed and clean this up a bit. So that's what that is called for resampling. Block resampling is using statistics, so it's not something that you have to calculate. You will just put it into a tool and it'll use a majority statistic like the mean or the maximum, something like that. We can also do what's called nearest neighbor resampling. So it grabs the value from the old cell at the center of the new cell. So say you had like overlap, so wherever that overlap is, it will use that center. We'll also have what's called bilinear resampling, and it calculates from the 4 cells closest to that one. And then cubic is when it calculates all 16 cells around that point. So this is all done by a tool. You don't have to do this. So why would you even do this? Because if you have 2 rasters that are completely different resolutions and you need to project them together, this is how you kind of correct to make sure you can not lose the accuracy of it. Storing raster values is all about bits and bytes. Okay, you need to know the basics of this. So bits are in sets of 8 called a byte, and you can store them from 0 to 255. Okay, more bytes are added to store larger numbers. So you know how you have like gigabytes, terabytes, petabytes, right? That's the concept. Pixel depth. So one value, or one byte rather, which is 8-bit pixel, stores any values from 0 to 255, and so on. Floating point values are required when we have decimal number storage. So you use that 32-bit pixel or 4 bytes. These are just things that you need to have in the back of your mind. Do you have to memorize them? No. So we have a band, which is called a single raster. Okay, and so that's like one single picture. You can have multi-band rasters that contain multiple raster arrays with the same number of rows and columns, and they're stored together as a stack. So a lot of times this is what we get with satellite images, and you stack them together. So above you can see that there's 7 different pictures of the same thing, and they're all in different wavelengths and brightness. So depending on what you need to see, that's Crater Lake in Oregon, you can use the different images, or you can put them all together. When you want to look at multi-band rasters, so you can change the color. So on the far left, or A, is the kind of natural color vision, right? Then you can see what's called false color or infrared in the middle. And then the last one is called band 7. So it allows you to pop different concepts or different things that you want to see based on the light reflection. Okay, that is kind of something important to know. Compression is just when you want to reduce the storage size. It is reversible because you can open it back up. If you use something called truncating, you do lose that and you cannot recover the values, just as a heads up. So data rasters versus picture rasters. So data rasters are going to be things like elevation, imagery, land use, roads. Picture rasters are really just pictures. It's like you scan it in and it's there. You can't analyze it. It's just a photo, like a base map. Excuse me. So rasters have coordinate systems just like everything else. Um, they come in GCS to start with, okay? And a lot of times things will be in a conic coordinate system. So you can usually find them projected in a coordinate system that makes sure that the area and the distance doesn't get messed up. But you have to be really careful because this is now, if you project it incorrectly, you can see between A and B a very large difference, okay? So in a GCS, at the top, it has a very different shape and very different rows of columns than in the DEM, okay, which is the digital elevation model. In a conic system, you see those measurements are going to be really different. So you have to pay really close attention to what your projection should be based on the area, right? When you project it, instead of using just the regular project tool, you're going to use the project raster tool. So it's the same steps, okay? It will take longer to run, so just as a heads up. We can also do something called georeferencing rasters. This is something that I did as a job, my first GIS job in undergrad. So you take a picture that's taken, like an aerial photo, and then you take an old picture and you line them up and you find the different data that kind of lines up. So it's ground control points. This is what a lot of times you'll hear called ground truthing. This is how you transform the real world data and build data together. Okay. A lot of it is math that you don't have to do if it's done by the computer. We can take cool things like 3D data, and you can see the elevation. So at the top, again, this is Crater Lake, and you can see the uplift here where the crater is, and then the road is on top. You can do this and store it as 3D data. It's really, really fun to do this, and you will get to play around with it. You can also change 2D features into 3D, like the bottom picture, where you can rotate the map and go like this, and then you can see how tall buildings and things are. It's pretty fun. So we're going to use a lot of DEMs or digital elevation models. Um, you can symbolize them just like you symbolize vectors, but it's slightly different. We can use this for slope or aspect. This is really popular and common. So if you have volume, like, so when I'm trying to figure out like how much water is in the lake, right, or the river, you would measure volume. So you use a voxel, which is basically a raster with height. So it's not just length and width, it also has height, okay? So that way you can figure out the volume. Point clouds are kind of cool. So a lot of times LiDAR, which is this really fancy camera, produces a point cloud set, which is what it looks like there. So you have X, Y, and Z points. So it's, basically 3D, okay? And so it shows in this picture all the different 3D images, the bridge, the river, the buildings and whatnot. And we have something called triangular irregular network. It also stores X, Y, and Z, but it uses nodes. Nodes is a vector, right? And it kind of basically puts little triangles around linear edges of things, okay? But this is how we can use 3D surfaces with fewer nodes, and then you use more nodes for like really steep areas, kind of like a topographic map. When the lines are really close, it means it's really steep. Similar concept. We also have something called multi-patch features, and that is what we use when we want to do like a building or a water tower. We have something cool called space-time cube. This is actually really fun. You can use an attribute to display like the changes basically in your map. So you do a spatial analysis. This one is about earthquakes, and the darker purple shows where there's been the most intense shaking. So that's kind of cool. So basically, it's a visual graphic, which is kind of fun. Some people really like these. Some people have a really hard time like seeing 3D, so you have to be aware of your audience. This is how you create a space-time cube. It's kind of fun. I don't think we're going to do this in class, but if you want to play around with it, in this book, in the manual in the back, you can walk through and figure out how to do this. When you're storing your raster, this is really important. GIS can only read 4 different formats, and so it either has to be in a file geodatabase raster, a TIFF file, Iridesc, or GRID. Okay, GRID is the old format, but it's fine. You can display JPEGs and PNGs and whatnot, but you can't analyze it or save it. because it doesn't understand what that is. When you open up a raster table, you're going to have the automatic object ID. That doesn't matter, but then you have value and count. So the value is a square that is the count of 1, and there are 29,190 squares that have the value of 1. It is actually alluvium, so that's like the one field that gets put in there. It's the name of the geological set. When you have no data, it's usually a 0, okay, and it can be a valid like measurement for elevation or precipitation because it either didn't rain or we're at sea level. um, this is a picture of South Dakota. So the DEM itself has no data outside the outline of South Dakota, and that's why it's white in the background outside of the state. All right. So that's it for my raster discussion for that. All right. Thank you for listening. Go ahead and go through the quiz to answer the questions and make sure you're reading. Hopefully, I will see you on Wednesday if I can get rid of this cough.